right? So we can flip the row and the column vector. So the second one is a conjugate matrix. Third one is a transpose plus a conjugate. And today we would like to mention the following four matrices. Number 4 is a symmetric. Number 5 is skew symmetrics. Number 6, dimension. Okay, so today I would like to mention the 4 spatial matrices. And the first two are relative to symmetric matrix. The first one is symmetric, and the second one is skew symmetric. So I would like to come up with an example to for better understand the difference between the two symmetries. So maybe I just Okay, let's look at the symmetric matrix. The definition for the symmetric matrix is that the transpose matrix equals to the original matrix. So if you exchange the row with the column, then it's called a transpose matrix, right? So if you find the transpose matrix equals to the original matrix, is a representative symmetric matrix. So we can check the element here is 3 plus phi I, right? So at this position should be so if you click the first row into the first column, so the element should go to this position. So similarly, the element of -6 will go to here. And this element will go to here. So you can imagine the matrix, all the elements in the matrix have good symmetric behavior. Similarly, the explanation for the skew symmetric matrix is that the A, T, just for matrix equals to -A. So only one difference between the symmetric matrix and the skew symmetric matrix. So similarly, we can check all the elements. So the element here that goes to the first column is additional minus 10. Okay. Similarly, this term that goes to the first column, the third row with minus 10. So it should be 2 minus 6R. So this term refers to the second column, the third row. So it should be this. So I think that it's quite easy to understand the definition of a symmetric matrix and a skew symmetric matrix, but it's very helpful for specific courses in material science because in different kinds of materials we have a different periodicity for the unit cell. So in the future, we can use these properties to handle the material with specific force, strength, or deformation. So I think it's very easy but very helpful. Okay. So let's move on to the number 6 formation matrix. And similarly, we would like to learn skew formation matches together. In contrast to symmetric matches, let's look at the definition first. The definition for the Hermitian matches is that if the transpose plus conjugate matrix equals to the original matrix, or you can describe the matrix with this format. Different textbook will show different labels. Okay. So if the matrix perform transpose and concurrent conjugate, then it equals to the original matrix is called the Hermitian matrix. Similarly, the definition for the skew Hermitian matrix is that if the A star or you can call the transpose and the complex conjugate equals to minus matrix A. So it's the definition for the skew Hermitian matrix. So we would like to use two examples so that you will better understand the matrix. Okay. So let's compare the two definitions for the Hermitian matrix. On the left, the transpose and conjugate matrix equals to A. So you can check the element in the diagonal axis. It should be real number, right? So you can find the characteristic of the elements in the diagonal axis. In contrast to the Hermitian matrix, elements in the diagonal axis for the skew Hermitian matrix, the definition is that So the element should be 0 or complex elements here. Okay, so the first issue I would like to highlight. Okay, so I think it's quite easy, but so we just use an example to explain for the Venetian matrix. So this term should be, so the transpose means the first row will swap, is changed to this side. So it should be 3 plus 5i, but we should have complex conjugate. So it should be 3 minus 5i here, right? So this term is a real number, so it's the same to this complex conjugate. So we will go to this side, right? So this element, complex conjugate of the element should be positive 3i, right? So after transpose operation, it will go to this side. It should be positive 3i. Okay, so it's a representative Hermitian matrix. Okay, let's move on to skew Hermitian matrix. So for the definition with minus 10. So we found that in the diagonal axis, the element should be 0 or you can find the I in the diagonal axis. So for the element 3 plus 5i, the complex conjugate would be 3 minus 5i, right? So if we include the minus 10, so it should be okay. The complex conjugate to 6i should be minus 6i, right? So with minus 10, so it should be so for this term, the complex conjugate to minus 7 is a real number, so it should be same with an additional minus 10, so it goes to 7. Okay. So I think it's quite easy, but if you go to specific courses, you will have a lot of complicated definition because it's very helpful to handle a lot of unique properties. Okay, so it's some special matrix we mentioned in the first part for the background information for learning the linear algebra. Okay. So let's move on to N.2. So I would like to talk about equation how can we use a matrix operation to solve equations. It's also called Gauss eliminations. Okay. Okay, let's move on to the second part in this chapter. Is relative to the Gaussian elimination. In the textbook, it's mentioned in chapter 8.3, page 396. Okay, so matrix could be used to handle to solve the equations. So I think most of you will be familiar with the equations. So it's very simple. We have three equations to solve the three variables to get the unique solution of the three variables. The method is that we can use equation number 1, multiply by the -2 and +2 equation number 2. The reason is that we want to cancel out the this term to create more zero term, right? So here we would like to describe this operation with matrix. So first, we would like to create a matrix called the coefficient matrix. So you just have the coefficient. For example, here, 2, 4, -2. 4, 9, -3. -2, -3, +7. Okay, so the three equations could be described with the matrix. So the matrix A could be called as a coefficient matrix. So you compose it with a coefficient in the equation, right? And here we can use a row operation to solve the solution. But it's only row operation is meaningful because the color operation is not meaningful. But it's for the in mathematics, both row operation and column operation are fine, a lot to use. But here, the application here is for solving the solution with the three equations. So it's only row operation is meaningful, right? So here we use this is called coefficient matrix. So so as you can see, the equation number 1 is that 2 equation number 1 is that 2x plus 4y minus 2z equals to 2. So that's how we rewrite the three equations with matrix. And the answer SYZ we can consider with a solution here or so we use a label to describe the solution. So you can consider like this. And later we will practice example for this. It helps us to get parametric format of the matrix. So now we just need to understand how can we convert from the equation to the formula, to the matrix operation. So and how can we solve this solution with matrix operation? We usually use augmented matrix, also called增宏矩阵 augmented matrix. What is the augmented matrix? Let's write down here. The augmented matrix is that if we include this term, it's called augmented matrix. So we can use we can perform row operations. So this one you can consider like this, right? So we can also the operation could be described with two descriptions. The first one is the first row times -2 plus the second row. The second row is the equation number 2, right? So you can use this description. The first row times -2 and the plus the second row. That's the two representative descriptions. Okay, and this term equals to R1 row, the first row plus the second row, right? The third row. The reason why we do this because we want to create more zero elements in the matrix. So this operation could be rewritten like this. The first row comes the coefficient 1 and plus the third row. So you can find a different description in different versions of textbook. Okay. So we can use the operation, and we can have this. So This augmented matrix is used could be equivalent to the three equation, right? So with operations, we can have the purpose why we do this because we want to get reduce echelon matrix 列减矩阵。This term is adjective 形容词 reduce row so the meaning is that we want to know the operation because I think the operation is easy and most of you understand how to perform operation. But this operation is meaningful for the matrix space because here is a very important idea. The space of the whiteboard is a two-dimensional, right? So you can imagine if we have vector 1, vector 2, vector 3 to vector 99. They are parallel and the vector 100 is perpendicular to the 99 vectors, and the space expanded with the 100 matrix, 100 vectors is a two-dimensional space. The reason why? Because only two vectors are linear dependent, right? They are 99 vectors are linear dependent. So the number of linear dependent vectors will determine the dimension of the space, right? So here, the linear algebra here, we have a matrix. So we have any row here. We can imagine row 1, row 2, row 99. For example, you have a 99 any number matrix, right? So if you have column 1, column 2, column so you have a lot of vectors here, right? So how many pivots here will determine the space we spend. So the matrix is a very interesting tool to allow us to handle the n by n dimension. N could be any number. So we can handle any space. And the reason why we need to perform the calculation, because we need to form the reduced echelon matrix. Because the reduced echelon look like you will have a lot of pivot through here. So what does the pivot means? In the column, other element should be 0. And this is called reduced echelon matrix. So the pivot number means the rank of the row, and the pivot number will determine the space of the matrix. So the reason why we need to perform the matrix operation, because we want to create the reduced echelon matrix. So it's very easy for us to identify how many numbers of the pivot. It determines the space we span for the space. So it's a very useful idea to help us to handle any dimensional space. So we can use the operation to help us to find a clear result. Here, the 2D space is easier to understand because we can compare the vectors. But you can imagine if we handle higher order space, it's very complicated. We only need the only thing we can be helpful for us to handle the higher order space is a matrix. So we can use simple software to handle the n-dimensional space. So we just need to find the linear independent vectors. So, for example, we have 100 vectors, but only 2 vectors are linear independent. So the dimension is 2, right? So if we have 99 vectors, but they are linear dependent. So the space that the 99 vectors span is only 1. So this is very important. The critical issue is that not the number of vectors. The key issue is that how many number of linear independent vectors. In other words, the linear independent vectors means the number of the pivot. How can we get to the pivot? We need to form the reduced echelon matrix. It's a very simple. So we can easily identify the number of pivot. And how can we get this? Because we need to use matrix operation. So it's a representative Gauss elimination. Okay. So later we will practice example for better understand of this. Okay. So we have a 10-minute rest. Okay, we would like to practice example in the textbook. Example 8.3. So we have 4 equations here. but we have 5 variables. So before we perform the operation, we can understand we will have arithmetic form. Arithmetic means 参数解. Okay. So we can use the method we mentioned before. We can let the equation, the 4 equation, could be described with matrix. So we just put the coefficient here. So this part you can consider as a coefficient matrix. And we would like to get the solution for the 4 equation. So here we usually use an augmented matrix. So we just include this column here. So the overall is called the augmented matrix. So this part is a coefficient matrix, and the overall is a augmented matrix. 增广矩阵, 系数矩阵, okay. So we can use a row operation. Only row operation is allowed for Gauss elimination because the column operation is not meaningful in this application. The column operation works in mathematics, but not work in solving the equation. Okay, so we can use a lot of operation. We can further demonstrate detail in the other example later. So in the example in the textbook, we can perform a lot of operation to get a reduced row echelon matrix. Reduced echelon matrix is called裂解 matrix. It's very simplified. As you can see, you can easily check the number of pivot. What's a pivot? There are 4 pivots. 输点。输我不会写。Okay. Okay. It's called a pivot. So, in the row, in the column, only pivot, you can find the only value at the pivot site with a union number of 1. So it's called a pivot. So it's easy to be obtained with operation, right? So it's very meaningful in handling the space that expanded in the 4 row vectors and 5 column vectors. So the space spanned with the 4 row vectors and the 5 column vectors will expand the 4-dimensional space. Because we found the 4 pivots in the reduced row echelon matrix. And here, another issue we would like to mention. At this point, we can use an operation like this. The row operation we can vector the first row times a -2 plus the second row to create 0, right? Similarly here, we can use we can flip the first row and the second row, and the 1 goes to the first row, right? Then we can vector the first row times a -2 to cancel out the second row to create the 0. So we can use a method to create a lot of 0 elements. So with this, we can get this is called augmented matrix. But at this point, how can we use this to describe the parametric form? So we can rewrite this matrix. I'd like to so this matrix is a reduced echelon matrix, so we can imagine this one. In this case, we have 5 variables: S1, S2, right? And because this column are all 0, so after any operation, it should be 0. Okay. So there are 4 pivots. The only column here is a non-pivot column, right? So here we would like to describe the 4 equations. The first one is we can use this. The first row times the first column. We can have S1 plus 1 plus S1 and 1 plus S1. Right? The second row plus times this column, so we can have S2 equals 0, right? And the third row comes the column, we can have S3 plus S5 equals to 0. And the fourth row will have this. So the 4 equations will become the 4 simplified equation here, because we perform the Gauss elimination to get the reduced echelon matrix. So we can simplify the entire system here. Okay, now we need to learn a new issue here. We would like to describe this with a parametric format. So here, we usually use let the non-pivot column equals to the coefficient to be determined. Okay, so with the assumption, then the first equation. So here we can get S1 plus C1 equals to 0, right? So it means S1 equals to minus C1. type. And similarly, the S3 plus C1 equals to 0. It means S3 equals to minus C1. Okay, so here, the solution for this 4 equation is what we want. Is this S1, S2, S3, S4, S1. So we can describe this. So the S1 equals to minus C1, right? S2 equals to 0. S3 equals to minus C1. S4 equals to 0. S5 is our assumption equals to C1. So here we can describe the solution with a parametric form. So we can let C1 comes out. So we can have minus 1, 0, minus 1, 0, 1. So it's called parametric solution. 参数集 okay. So it's a kind of vector because and C1 could be any constant. So in general, you will have infinity solutions, but the solution have a specific relationship. Is relative to the parametric form, 参数集. Okay. In this example, it's a very easy, very simplified case. So we would like to let all of you to better understand the operation. So we designed the new example here. So actually you can find a lot of examples. You will have a matrix. So you can also have some equations. So I think it is similar. So you need to add the matrix to solve the two issues. The first is AS equals to B. The other is AS equals 0. And it's very similar to what we learned in chapter 3. It's relative to homogeneous solution. It's very similar to the particular solution. So in linear algebra, the difference is that so I think maybe you just okay. So we just finished this example. So any question on this? If no, we just move on to this example because I need to use the space to explain this. Okay. So here is what we need to learn. The parametric form, because it's very useful. And it's a reason why we need to have reduced the algebra matrix, because it's easier for us to identify the dimension of the space and the matrix spans. The matrix will have 4 rows, so it has 4 row vectors. the matrix has a 5 column. So in other ways, it has 5 row vectors. So all of these vectors will expand the space in 4 dimensions. The number of the dimension of the space is termed with the number of the pivot. Okay. So let's look at this example. We have a matrix. We can have any kind of matrix. So the first step, if we want to solve the question number 1, we just let the matrix combine the B to form an augmented matrix here. I think it's very easy, right? So we just have an augmented matrix here. Okay. Then we can use the row operation to create a 0 here. So we can let the first row times and minus 2. So we can cancel out the element of 2. Create more 0 here, right? So after this row operation, it's the first row times and minus 2 plus the second row, we will get this. Okay, so you can see the third row is the same to the second row. So we can direct that the second row times a minus 1 and plus to the third row, then we can cancel out the third row here. So as you can see, we have third rows. In other words, we have 3 equations, but only 2 are meaningful because the third equation is linear dependent to the other 2 equations. Can you get the point? Okay. I think the operation is very easy, but we just need to learn the meaning behind the operation. Okay, so here we can get we try to get a reduced echelon because there are 2 pivots here. And what does a pivot means? We need to make sure the column only has the value 1 at the pivot site, and the other element should be 0. So for this reason, we need to let the second row times a minus 1 and plus the first row to cancel the element of 1. So we try to let the second row times a minus 1 plus to the first row, try to cancel the 2 elements. So we can create the 0 with operation. So this is a reduced echelon matrix here, right? So similar to previous discussion, we can let the augmented matrix we write as a equation. So here we can let the augmented matrix like this. So what does the AS equals to B means? So A equals to B means this. And what is this? It's a reduced echelon. And the solution is that that's the reason we would like to use a row operation to get the reduced echelon here. So here we can describe this equation. So similarly, S1. So the first row times the first column and equals to 1/2. So S1, so it should be 4 because we have 4 column, so it should be 4 elements in the column. So S1, 1 plus S1, 1 times S1 plus 3 times S2 equals to 1/2. And the second row times the column. So we will have S3 times 2 S4 equals to 1/2. Right? So we have the two equation here, and they are two dots, and we highlight they are two non-pivot color here. So we let S2 equals to C1, let S4 equals to C2. So we can have S1 equals to 1/2 minus 3 C1, and S3 equals to 1/2 minus 2 C2, right? So the answer, what we want here S1, S2, is that 1 half minus 3c1, s2 equals to c1, s3 equals to 1 half minus 2c2, s4 equals to c2. In most textbook, the answer is that. So here we would like to highlight the meaning behind the solution. So we can let C1 comes out. So C1 in this solution, so it should be minus 3, right, for the S1. For the S2 equals to 1, S3 0, S4 0, right? And if we let C2 goes out, so S1, S2, there are no C1. So S3 will have minus 2 C2. So S4 will have 1 C2, right? And finally, we could let the non-homogeneous term goes out. It's 1 half 0, 1 half 0. So you can further look at the solution. It's like a homogeneous solution, right? It's like a homogeneous solution with a parametric format, with parametric format too. This is similar to a particular solution, right? Because there's no constant here. So it's very, very similar to what we learned in chapter 3 for the non-homogeneous solution, right? But here, in this chapter, we are talking about the matrix. So it's relative to the matrix. If you look at, if you think, if you review the chapter 4, when we use infinity terms of the series, then the solution, homogeneous solution, goes to infinity terms. So the overall idea are very similar. So here we can have the solution. This is what we want. The solution is this. If we, example, want to solve this, means we need to get this solution. Okay, so let's further look at the second question. If AS equals to 0, and what you can expect the change between the two solutions. So the first one, the solution could be considered as a non-homogeneous solution. This one could be considered as a homogeneous solution, right? Because if B vector be replaced with 0, so you can imagine all the elements here will become 0. So any operation will not change the read 0, right? So any term will be 0 here. Okay, so it should be 0, 0. So this term will be 0. So here will be 0. So the second question is that the B column replaced with 0. So the augmented matrix perform the row operations, then everything will be the same, but this column will be 0 here. So we can have very similar formulas here. So we can get the solution. It looks like a homogeneous solution without homogeneous term. Okay. So I think it's very similar to what we learned in chapter 3. And the two parametric form is called Tanshuji. Okay. Okay. So we can use this to identify the space and the vectors in the matrix. So it's very useful to handle any dimensional space we want. Okay. Okay, let's move on to the other issue. It's called the Cramer's rule. We also mentioned this in chapter 3. In chapter 3, we call the Wronski. In this chapter, okay. So we mentioned this in chapter 3. We want to identify, or we want to verify the linear independency or linear dependency among the three different functions, f1, f2, f3. So the definition for the linear independency among the three functions is that the C1 should be equals to 0, should be equals to C2 and C3, right? So we need to understand, we need to get the unique solution of the C1, C2, C3. So in chapter 3, we use a Wronski to describe the coefficient of the f1, f2, f3, and their derivative, right? But here, we have a very similar description. Would you write it down? So if we have three equations, like this. So we can describe this previous the way we mentioned before. So we can have a coefficient matrix. The first row and the first column. Second row, first column. Third row, first column. The first row, second column. Second row, second column. Third row, second column. First row, third column. Second row, third column. Third row, third column. Right? So here we can have this one equals to the determinant of the coefficient matrix. And the denominator we can replace the first column with B1, B2, B3. So the second column will be like this. And x2 equals to this. The only difference is that and S3 equals to this. So here we will have three cases. The first case, we will have a unique solution, or we call the 恰有一解. If the determinant 行列式 of coefficient matrix not equals to 0. So the denominator is determinant of the coefficient matrix not equals to 0. It means S1, S2, S3 would be unique solution, right? The second case, we can mention third, but case number 2 and number 3 is a infinity solution and no solution. Okay, in the case, if the determinant is 0, so if the coefficient of matrix, determinant of coefficient matrix equals 0, you will have two cases. So we can imagine, we can use two examples to describe the two cases. The first one is if your solution is like this. In this case, equals to like this. Because the determinant of the coefficient matrix is at denominator, so this. So the determinant equals 0. So the answer here, we can calculate the determinant to get a number. If the number is 0 or non-zero, you will have the two cases. So we can rewrite the two cases for better feeling. So you can imagine 0 times x equals to 0, and vice x. It should be any solution, right? So you will have infinity solutions. So anything plug in the equation would work. And in contrast to the case, if you let the 0 goes to this. What is this? This is the denominator in the determinant in the denominator cancel. So the answer, or the solution for the equation, you cannot find any solution can work for this equation because 0 times anything equals to 0, right? So in this case, it should be non-solution. It's called 无解. Okay, I think it is very simple and easy. You just mention in this chapter, so we can understand. If we have equations, we can represent with matrix, and we can get the solution use Cramer's rule. And Cramer's rule we have three cases. The first is a unique solution. It requires the determinant of the coefficient matrix not equals to 0. So you will have a unique solution. And if the determinant equals to 0, then you will have two cases. One is an infinity solution, the other is a no solution. Okay. So this one in the chapter 3, you remember it's called Wronski. Okay, very similar, I think it's the same ways to describe this. Okay. So today we just start here, and next time we will talk about the determinant in detail for 2x2, 3x3, or more high order determinant. Okay.